Welcome back everyone to this lecture series on coding out decision trees with Python. In part 1, we formatted our data as well as visualized and explored it, and now we're going to move on to creating the decision tree model and exploring the model itself as well as the hyperparameters of a decision tree. Let's head back to the notebook. Okay, here we are at the same notebook where we left off in the previous lecture. Now let's go ahead and create a decision tree classifier just using the default hyperparameters. Then we'll set up a visualization function that will allow us to actually see in real time the effect of changing certain hyperparameter values. First, let's import decision tree classifier. We will say from scikit-learn.tree import, and then it's decision tree, and we're working with a classification task, so it's decision tree classifier. Then we'll create a model, decision tree classifier, and if you do shift tab here, you'll notice that there's quite a lot of hyperparameters you can adjust. Things like the maximum depth we talked about, the minimum samples allowed into a node before you actually split it, the minimum impurity decrease, etc. So we're going to use all the default parameters and then explore how we can actually find the optimal hyperparameters as well as just how hyperparameters can change the output of a decision tree. So we will just create our model, and then we're going to fit our model to our training data. We'll say fit xtrain and then ytrain. And let's get what I'm going to call our base predictions. And the reason I'm calling it base predictions is this is just essentially the base hyperparameters or default hyperparameters. So we'll predict off xtest features. So now I have my predictions, and if I take a look at my predictions, it's just a list of species of penguins, which makes sense. Now what I want to do is compare that to the correct answers, which is ytest. These are the correct answers for those index rows. So now let's actually do an evaluation. It's a classification task, which means I can say from scikit-learn.metrics import, and I'm going to import the classification report. So we'll say classification report, and then I'm also going to import the plot confusion matrix function. Okay, so again, classification report and plot confusion matrix that we've seen before. I will say print classification report, and we'll simply compare ytest to base predictions here. Run that, and I can see that overall I'm performing pretty well. I'm getting really good precision, recall, and overall accuracy. And this makes sense because recall, if we take a look at the visualization, we already saw there was clear separation between the different species of penguins. So I would expect really any machine learning model to perform quite well in this particular case. And what we can also do is actually plot out our confusion matrix visually. And we know that plot confusion matrix is going to take in the model itself. So we have our base, we have our model. There we go. And then it takes in xtest and ytest. Recall that the plot version of confusion matrix takes a fitted model and then your x feature test set and your ytest labels to actually compare to. So run that, and you will see how many samples you're actually messing up here or getting correct. And you should be getting pretty good performance. Depending on how you actually ran your decision tree, you may get something very slightly different than this. But you should see at most probably around 3 penguins being misclassified, which is pretty good given that most of the penguins are being classified correctly from the test set. Now, one of the strongest benefits of using a decision tree learning model is that it's very interpretable by a human. And in fact, it comes with lots of useful attributes after it's been fitted. We can call model.featureImportances, run that, and it will report back the relative importance of each feature in its decision making. And this is listed in the same order as the X feature. So if you take a look at X here, we have these columns, or x.columns. And this is the feature importance for the relative feature that was passed in. I like to format this as a data frame. So let's go ahead and do that. That way it's going to be easier to read. We can say data frame, set the index to x.columns, set the data equal to this model.featureImportances, and then what we're going to do after this is go ahead and just set the columns names. So we're going to say columns equal to, and then pass in a list string or whatever you want to call this. So I can call this feature importance. You can choose whatever string you want here. I'm just going to label that column of model.featureImportances. Running that cell gives us the following result, which is essentially just a combination of what we had up here, the numbers, and then the lined up index, which is the column names. Now, I like to actually sort this so I can see which were the most important features for this particular decision tree, in which case what we're going to do is simply say sort values. And be careful, you don't want to sort by the index. I would do it alphabetically. I actually want to sort by this single column, feature importance. So let's copy this string and then paste it in here. So sort values by feature importance, run that, and then you should see that the most important feature for this particular decision tree was actually flipper length. Now you may be thinking, how is it not even considering things like island or the sex being male, or not even really considering the body mass? And that's because of the way the tree was constructed given the hyperparameters we let it run, which means often it's not actually going to even consider all the features unless you really push for the decision tree to try to use all the features. Keep in mind that could always lead to overfitting on your training data set. In order to really understand what's going on, it would be nice to actually visualize this tree. And luckily for us, scikit-learn, the most modern version of it, actually comes with a really useful function called plot_tree from sklearn.tree. So import plot tree, and what this does is you could just say plot tree, pass in your decision tree learning model. It can't just be any model, it has to be a decision tree. Run that, and it will output a bunch of text values, which is kind of strange, but if you scroll down, you'll see this tiny little figure, which is the actual decision tree that we fitted. By default, this isn't very useful, so what I like to do, especially if you're working in the Jupyter Notebook, is if you put a semicolon after anything in a Jupyter Notebook, it won't print out any resulting text, it'll just print out the image. Now this is quite blurry, so what I also like to do is up the DPI as well as the figure size. So right above this, we're going to say plt.figure, and just as we've done a bunch of times in this course, we'll say fig size is equal to something larger, maybe 12 by 8. And let's also increase the DPI so it looks a little nicer, like 200 DPI. Run that, and now we see a really nice decision tree. Now let's talk about what these values actually represent inside each node of the decision tree. We can see the very first line here, x2 less than or equal to 206.5, is telling you that it's grabbing its feature data, x, and then grabbing the column 2, or at index 2. Recall, indexing starts at 0, so it's technically the third column, 0, 1, 2. And if we take a look at our original training data, so x, or xtrain, here, 2 is going to be flipper length millimeters. And if you come back up here, recall flipper length millimeters was the most important feature for this particular decision tree. Keep in mind, we can always add in hyperparameters to build out another decision tree. But the reason this one had so much importance was because it was the very first feature that it split on, which makes sense, x2. And something that's really nice is we can actually give these feature names instead of saying x2 by saying plot tree, and there's a feature called feature names as a parameter, and then simply pass in x.columns. Because we know this is in the exact same order as the x here, if we run this, it will replace, scroll back up here after running it, it's going to replace x of 2 there with the actual string, flipper length millimeters, which is a lot easier to read in my opinion. And the other thing you can do is say filled is true. So we can say filled here is equal to true, and it will actually color these based off what feature is being considered. So this is what I would say the default way of using plot tree is. Make it a lot larger, make it a higher DPI to really see clearly here, and then also passing your model with the feature names, easier to read, and filled in, just makes it a little nicer to actually visualize here. So we know this first row value, flipper length, millimeters, that's the feature it's considering, as well as the split it's actually considering. Then we see the Gini impurity of that particular feature at that particular split. So just like we saw in the theory and intuition lectures, scikit-learn is actually performing that mathematics behind the scenes. Then we see samples is equal to 233. What does that actually mean? That is the number of samples that are entering this particular node. So this 233 makes sense as the number of samples. Well, let's go ahead and check that out. If we say xtrain and check the length of xtrain and say 233 here, that makes perfect sense because all your training samples are going to enter the first node and then they're going to get split. So 147 went to the left and 86 went to the right. And then if you see this value array, 105, 45, 83, that is simply reporting back the labels as they're being entered. So 105 plus 45 plus 83 is equal to 233 samples. But that essentially tells you you have 105 of one species, 45 of another species, and then 83 of another species. So it keeps track of the labels as you continue. And if you have a leaf node that only has 0, 0, and then all the numbers in a particular species, that means it's perfectly classifying. So it makes sense that the reported Gini value for that will be 0 because it's pure data. It's classifying that perfectly. Okay, so now what we want to do is explore and understand the hyperparameters, but it would be nice if we could write all of this in a function so we could always report back the model visually as we begin to play around with those hyperparameters. Let's set up that function now. So I will scroll down here and I will say def report underscore model takes in a model. So we will create a new model with different hyperparameters, and then I'm going to get those model predictions. We'll say model preds is equal to model predict off the same X test set that we had last time. That way I can compare everything. And then we'll print out a classification report. We'll say classification report Y test model preds. Then I'm going to print a new line. And then let's visualize that tree. So I will simply copy and paste the 2 lines of code here, plt figure and plot tree. Copy that and paste it in. Make sure that's lined up correctly with indentation. Run that. And so this is a convenience function for us where I can say simply report model, pass in a model that's been fitted on training data, run that. It's going to tell me my classification report and give me this nice decision tree. Now I can really play around with the model hyperparameters and see how it affects everything, as well as see how it affects the actual decision tree. Here we have the default hyperparameter options for the decision tree. And what we're going to do is simply play around with this to explore how the different hyperparameters actually affect the tree. I would highly encourage you at this point, open up a new tab with the documentation page for decision tree classifier to read more about the details of each hyperparameter available to you. We're just going to be going over the main and most important ones here. The first hyperparameter we're going to explore is setting a maximum depth of your tree. If we take a look at this default hyperparameter tree, we have many levels of splits. In fact, we have 1, 2, 3, 4, 5 levels of splits. This is a depth of 5. You're counting the number of splits as you go down the tree. So what we're going to do to really visualize this is create a pruned tree where we set a mandate for this decision tree that we're only going to allow a max depth of 2. Just 2 levels of splits. So we create that new model, pruned tree, and I grab pruned tree and I fit it to my training data, just as before. We'll say fit on X train and Y train. And then I will report model, pruned tree, run that, and I get to see my classification report. Right off the bat, you should notice a slight decrease in performance. But if you take a look at the decision tree, it's actually a lot simpler now. It's only considering a few number of features. In fact, we only have flipper length, and Coleman depth for this particular tree. So it only considers 3 features, and you should notice it has a maximum depth of 2. So there's this first level of splits, and then there is this second level of splits. Do not confuse depth with number of splits allowed. It's how many levels of splits are you allowing here. And you can continue to play around with this. So we could come back up here and set a maximum depth of 3. Run this again, and then it'll slowly start expanding this, and now we can see there's 3 levels allowed. Keep in mind though, if you were to set a maximum depth of something much larger, let's say 13, and run these all again, that doesn't necessarily guarantee that you're going to get 13 as a level of splits. Really what this is doing is just setting a maximum limit. It's not a limit of depth that you must reach. So if you start setting too large of a depth, you're really starting to just hit the default tree here. And if you want more information about the default maximum depth, we can say help on decision tree classifier, run that, or check out the documentation. Scroll down here until you get to maximum depth. By default, it's none, and it says if none, then the nodes continue to expand until all the leaves are pure, or until all the leaves contain less than minimum sample split samples. Essentially, how many minimum sample splits must we allow in order to continue to splitting to a terminal node? So you can also edit this here. Minimum samples split, the minimum number of samples required to split an internal node. So you'll need at least 2 samples entering to begin to split that again. Obviously, this is something you can play with as well. Now, what we're also going to check out here is the maximum number of leaf nodes. And we can think of these different ways of setting hyperparameters, like setting a max depth of 2, as trying to avoid overfitting to your training data. Clearly here, with max depth of 2, we're not going to be able to overfit because a tree cannot expand to such minute detail of the training data. In fact, we're only considering really 3 features here. And obviously, we would want to use cross-validation to test out a grid parameter search of different depths to try and different other hyperparameters. Let's move on to this maximum leaf nodes. So we are going to say here, let's say max leaf tree. So max leaf tree is equal to decision tree classifier and set the maximum leaf nodes equal to 3. Remember, we only have 3 species, so this is really going to constrain this tree. So we will say max leaf tree. I'm going to fit this to xtrain and ytrain, and let's call report model on max leaf tree. Run that, and you should notice quite a bit of a drop in performance, but take a look at this tree, how simple it is. This is only allowed to have 3 terminal nodes, and since we only have 3 species, it really can't do that many splits. Now it's only considering 2 features, and for the performance bang for your buck, so to speak, for features, it's really performing quite well, considering it only ever did 2 splits, and it has the absolute minimum value of terminal nodes here in order to correspond to 3 species. So the Gini values for even one of these is actually 0, which means it's doing a perfect split here for one of these species of penguins. And it's actually not misclassifying that many here. It misclassified a total of about, let's say, 7 plus 1, 8, 9, 10, 11, 12. So not bad considering that we're only allowing 3 leaf nodes. During the theory and intuition lectures, we also talked about different developments in decision tree, including Quinlan's analysis to use information gain as the criterion instead of Gini impurity. Now, we won't actually go through the mathematics of information gain. You can check those out on the Wikipedia article for decision tree learning if you want. But what we can do here is create an entropy tree and say decision tree classifier, and the criterion is going to be set to entropy, which is also known as information gain. By default, it is set as Gini impurity. So all we're doing is we're deciding a different mathematical criterion for that actual split. So instead of Gini here, we're going to see the entropy value. So run that, and then we'll see entropy tree, and we will fit this to xtrain and ytrain, and then report model to the entropy tree. Run that, and you'll notice that we're actually performing quite well. And we could also perform a confusion matrix here to see how we compare. But what you should notice right off the bat is this tree will look something different than Gini impurity, hopefully, depending on what your actual data set is. So you can begin to compare the actual split values here to, if we scroll all the way back up here, our original default parameter. So notice here on the left, we're saying Coleman depth millimeters less than or equal to 16, Gini of 0.245. Then scroll all the way down here. Now that we're considering the information criterion, you'll notice it's actually considering sex as male over here, or what island it was. Interestingly enough, it will still have some body mass grams at a very similar cutoff to before, but now we're just considering entropy value, or information gain, instead of actual Gini impurity. Essentially, just a different mathematical equation of considering how we're actually going to split these values. All right, so we're going to end the lecture here. Something I do want to really note is that I highly encourage you to check out the decision tree classifier documentation and just explore the parameters. Most of them are self-explanatory, like max depth or minimum samples to split, and then you can begin to explore how you yourself could begin to change this and use that report model function to visualize the changes yourself. I really think that's the best way to learn decision trees, is to just play around with that report model function on various values you can provide for the hyperparameters. Typically, you'll perform a grid search for the best hyperparameters, but we're not going to do that right now because in general, the actual misclassifications we're performing without a grid search is quite small, and the default values are performing just about as well as you could possibly hope for. Recall that if we take a look at our original decision tree, as well as the plot confusion matrix function for it, so this original decision tree, if you were to report the model on it, it's performing really well at 97% accuracy, not too much precision and recall, and we were only misclassifying about 4 penguins. Even if you did an exhaustive grid search, you'll probably still misclassify 2 to 3 penguins. So not a huge jump in performance considering the default hyperparameters are only misclassifying 4, which is why we won't go through the whole rigmarole of running a grid search. But realistically, on a large data set that is harder to classify, you will want to do an exhaustive grid search with cross-validation, just as we've done with many other models before, in order to figure out what the best hyperparameters are. Okay, now decision trees themselves are prone to overfitting, and we already know that there's many developments that expand off a decision tree model, such as random forests or a gradient boosted tree, to help expand the decision tree model as well as fix some of its potential flaws. And that's really where we want to head towards, the more advanced tree-based methods that are built off the decision tree. You don't see a single decision tree used that often due to the fact that there are now better and more robust methods like random forest and gradient boosted tree, especially for more realistic data sets. So let's head over to the next section where we begin to discuss random forests. I'll see you there.